Okay, my friends, before we go any further, please go in and open up that caffeine article that's in Canvas right next to this playlist. In it, you'll find a little tiny synopsis of a research study done on professional cyclists and ingestion of caffeine. Read that bit and then come back. Okay, friends, now you've had a chance to read the synopsis. And again, it was a synopsis of the article, not the entire thing. I tried to cut as much out as I could that was jargon laden and focused just on the statistical results, which are right here. This one sentence here. It's a bit of a wordy sentence because it talks about, the dosage of caffeine and the range of the heart rates and a bunch of stuff like that. But the P values are the ones I really want to talk about. That P is less than and P is greater than 0.05. Okay, let's back up and remember about these hypotheses and how the p-value ties to them. Okay, so first off, the research hypothesis is what the researchers are trying to test. The null hypothesis is going to be the opposite of that. And the test is actually what we do to decide whether we believe the null hypothesis or the research hypothesis. Real quick, I wanted to do some chalkboard time here. I had the research hypothesis defined first in this PowerPoint, followed by the null. I wanted to make sure that when you formally list out the hypotheses, the null always goes top, research bottom. At least traditionally, that's what happens. Although the paper the reason you're reading this paper is because they supported the research hypothesis, which is surprisingly that caffeine lowers heart rate. Now, granted, technically speaking, this is like 3 studies in one, because they studied the effects of caffeine on rest cycling, sub-maximal cycling, and also maximal cycling, which means we've still got to concern ourselves with the same thing we did with multiple confidence intervals, but let's deal with that later. We'll deal with that later, I promise. That's a big part of the end of this course, is making sure we look out for things like that. The null hypothesis is the opposite of caffeine lowers heart rate, which is caffeine does not. Caffeine does not lower heart rate. I mean, when you think of caffeine, you probably think of something that raises heart rate. It's a stimulant, right? But the opposite of lowering heart rate is does not lower heart rate. So these hypotheses right here were tested 3 times in this study: at rest, at sub-max exercise, and at max exercise. Okay, let's go break those down one by one. Now, there is one little bit I want to chat about here. They mentioned the word placebo, and I just wanted to make sure that we understood that placebo, what the importance of a placebo is. Okay, so basically, caffeine is given or was given to these athletes in the form of a pill. Okay, so you can't just give some of the folks in the study a pill and not give others a pill, because psychologically, they might think because they're getting a pill that they're being given something that's going to impact their performance. So that means everybody has to get a pill. You have to trick the mind a little bit, and that's what a placebo is. A placebo is a pill with nothing in it. It's fun. You have to trick the mind a little bit there. Okay, now, as you saw in the hypotheses, you always start by assuming the opposite of what you're trying to show. Now, what I mean by that is the researchers want to see that caffeine impacts heart rate by lowering it. So they start by assuming it doesn't. And just to drive home a point as to why that makes sense, why you should start by assuming it doesn't, you can get these athletes' baseline heart rates without using caffeine. I mean, they're easily measurable, right? So once you've got that baseline heart rate, you can build a sampling distribution, we're about to, around that baseline number. What kind of blows me away is who thought in the first place that caffeine ever would lower heart rate? It's a stimulant, right? So, I mean, I don't know, maybe these guys are sitting around on a Saturday on one of their long rides, and halfway through they stop at Thump and man, like if I have that extra snort of espresso in the morning, I don't quite get as gassed on Archie Briggs as I do otherwise. I could almost hear him saying that. But the point is, you start by assuming the opposite of lowering heart rate for two reasons. First of all, why would it? But more importantly, we can form a baseline on these cyclists without caffeine in their system. All right, so caffeine significantly lowered heart rate during all three sub-maximal exercise intensities. So that's like you're pedaling hard, but you haven't gotten to your limit yet. So caffeine lowered heart rate. Again, based on the video we just talked about, that's surprising, right? Why would caffeine lower heart rate? Especially when you look at the rest riding, which is just very comfortable riding, not pushing yourself at all. Caffeine did not lower heart rate then. That's what you can tell by that one p-value right there, the p-value bigger than 5%. Or maximal exercise, going all out, also bigger than 5%. Okay, so there's three p-values right here. I want to make sure we remember what those p-values are, and I use a capital P because I love you all. Okay, so p-value is a probability. That's what the big P stands for probability. It is the chance that you got the data you did, or even more extreme data, assuming the null hypothesis is true. In this particular example, we're talking about caffeine, and we're looking at the chance that we got the heart rate data that we did, assuming caffeine had no effect. Now, let's break this puppy dog down into the three exercise levels. Submax, which was the interesting one. That's, by the way, why you're reading this article. Then we'll look at rest at maximum. Okay, so caffeine significantly lowered heart rate during all three submax exercise intensities compared to placebo. Okay, now this bell curve right here is pretty much identical to the one we looked at on the board for the cursive versus typing brain development one, except you might notice that the confidence interval represented in the bell curve doesn't have two sides. And the reason for that is pretty straightforward. The researchers want to show not just that the heart rate was different than what they expected, but that it lowered it. So this is called a one-sided confidence interval. You don't have to worry about this. We're going to get more into this next week when we actually do our own studies. This is a one-sided confidence interval. That curve still captures 95% of the area, but the area is all on the right-hand side. That is where normal or elevated heart rates would be if you took caffeine. So in other words, suppose you took caffeine and nothing happened at all. That means you would land right about here. If you took caffeine and your heart rate elevated statistically significantly, your heart rate would go up this way. But if you go far enough this way, that means you're in unusually low heart rate categories. And that is what happened during sub-maximal exercise in this study. They saw surprising results. As a matter of fact, we can quantify it. There's less than a 5% chance that we should have seen heart rates lowered, at least as extreme as we did, if the caffeine wasn't causing the lowering. Hey, Chalkboard Sean's back. As I'm editing these videos, I'm realizing little things that you might be thinking of. A lot of times my students in class think of things like, well, okay, their heart rates are lower. What else could have lowered heart rate besides caffeine? Is there a dietary supplement they were taking? Is it physiological and not chemical? Could it be some kind of a training regimen? This is a stats class, not a research methods class. So we are giving them the benefit of the doubt that the only difference across all the athletes that they surveyed in this study was that some of them got the placebo and some of them got caffeine. Everything else we assume is the same. Is that a fair assumption? Yeah, maybe not. But this is not a research methods class. I have to teach you hypothesis testing in 3 weeks, which basically means I can give you the mechanics of hypothesis testing. Matt Novak teaches an entire full-term research methods class that talks about how to seriously control, drill down to the most microscopic level. So we have to assume, I'm always going to talk about the potential for things to get hung up on, but we have to assume that these studies were done controlling for every variable except for the presence or absence of caffeine. Is it ideal? Yes. But 3 weeks, y'all. 3 weeks. Okay, let's get back. Okay, now let's look at the two p-values that were large next. Okay, these were the at rest or maximal exercise p-values. Notice how they're both greater than 5%. That means whatever statistics they got for the at-rest and maximal exercises landed within the 95% confidence interval for usual or elevated heart rates. I'm not exactly sure where because they don't tell you about that. We're going to talk more about that towards the end of the course, the fact that they don't tell you about these large p-values in great detail. So in other words, you took caffeine at rest and your heart rate didn't go down. Not surprising. Not surprising. It's caffeine, as we said before. It's a stimulant. Also, at maximal exercise, your heart rate did not go down. Also not surprising. You took caffeine. So, in words, here's what not at rest is going to look like. There's a large chance that we could have seen the heart rate data that we did if the caffeine had no effect. Also, looking at maximal exercise, same exact thing. There's a large greater than 5% chance that we could have seen the heart rate that we did if caffeine had no effect. Some students get a little hung up in the language. So rather than kind of writing it this way, I've also, well, here, let's just go to the big idea. This seems to help students a lot. Large p-values simply imply that when you did your study, nothing unusual happened. So the null hypothesis appears to be true. That's why large p-values land, or at least imply, that your data comes from a distribution within the sampling distribution's confidence interval. Generally speaking, they're bigger than 5%. Generally speaking. Now, the big idea continued, which is a little bit weird because this is about small p-values. Small p-values, everything is opposite. Whatever you're studying had a measurable effect because it's too hard to believe that what happened occurred due to randomness and not whatever you were measuring. So what small p-values show is that your data landed outside the confidence interval based around your null hypothesis. Generally speaking, they're less than 5%.